So hi, so this is my wall clock, and if you listen carefully, you hear it ticking, and I wanted to know how much amperes does this clock draw from my 1.5 volt battery that I'm putting in, and it's still working like a charm, even though the battery is in there is like half a year or a year. And I wanted to know also not only how much current, but also how much voltage does the battery provide, because this clock really works to the second. I have let it run for a year now without any intervention, and my iPhone still shows exactly the same time as this clock. It's amazing. So let's look at how much power this thing draws. So I put the clock into a stable stance with like this construction. And let's take the battery out of here. So. And I have used my 1.5 volt battery tester here. And let's look at the battery, and it says 1.33 something, and it says good. So after even from half a year to a year, and still the battery is good from the clock. So let's be good. Let's write down the voltage. U equals U of battery equals 1.336 volts. Okay, and now up to measuring the current that flows through the clock. So what I've done here is to connect this positive crock clip to where the positive battery lead has to come, and I'll connect this end then to the battery, and then the negative end also to the negative input of the clock, and then here we'll collect the other side. I most probably will do the battery in series with an ampere meter, so we can easily read how much ampere are flowing through it. So that's the setup. I'll just to tinker a little bit to get a measurable amperage here out. So that is kind of an inventive setup. We go from the battery via plus here to this connector. We follow that line back into our multimeter. We go then out of the multimeter through this line here to the plus pole. So we connected the plus pole, the battery through the multimeter and some to here. And then we go out from here with black cable. It's a little bit of a construction, and then we follow the path to here to this connector, and then this connector here connects to the negative terminal of the battery. So in sum, we connected the battery via this multimeter to our clock. And as you see now, I have switched the multimeter on, and it has really a hard time of measuring the current. You hear the clock ticking, but it just sometimes it rises, the display rises to some amount of milliampere, and then again not, to like 1.35, 1.36 we had peak, giving the impression that when the mechanism is not working, that there is no power drawn. So just every second with the clock tick. I think we have to invest there further, but first indication is around maximum 1.3 milliampere. So I would like to write that down, but perhaps we have to go deeper on this one with kind of an oscilloscope, but not yet have the full idea of how to. But let's write that 1.3 milliampere down max. So I've written these down. The current to the clock is 1.3 milliampere. And then we can calculate the power that the clock consumes, because we know a battery has 1.336 volts, and it gives 1.3 milliampere flowing through, and it flows through the clock, this 1.3 milliampere. If you multiply the current and the voltage together, you get the power. And this is this 1.7 milliwatts then. But as we've seen, every other second only, the second where the clock is not moving, its handles, then there's no power consumed. So I think we can say 1 second no power, and in the other second this like maximum reading we did 1.7, like as we could do it as close it is possible, as coarse as with our digital multimeter. And so that's when this clock is active in the second, and in the other second it consumes no power. So I think we have to divide that by half, and then we would land about at 0.85 milliwatt. So not milliwatt then, but 850 microwatt. Oh, that's some kind of thing. So the power divided by 2 we can write would be 850 microwatt. And then that's the one thing. And if you see the battery life, okay, how much milliampere hours are in it, then often you have something like on a 1.5 volt AA battery, there's something like 1500 milliampere hours. And if you see this this current drawn by the clock, we have only half of it again seen over the whole time, because half of the time there is no current flowing. So this would be then half would 650 microampere. So 650 microampere. And then if we wanted to calculate how long in hours our battery can drive this clock, how long the clock will be active, we can just divide that 1500 milliampere hours by 650 microamperes. And what comes out there, let me quick calculate. And so there comes out 2.3 times 10 to the third hours, because you have your micro down below and milli up, and milli is much larger than micro, so by a factor of 1000. And 2300 hours, I mean, a day has 24 hours, right? And so you can say with these given numbers, it would suggest us that how many, if we divide this by 2300 hours by 24 hours, how much hours would that be? Naja, not quite, but roughly 100. So, but about 100. So this would mean this clock can run with this battery only 100 days. But as I said, a year has 365 days, and I said I have run it now half a year, so at least 180 days. So I think there's something wrong with our reading of the digital multimeter, and we'll have to step into the oscilloscope. So first thing for measuring the current with the oscilloscope is we need a defined resistor over which we measure voltage, and then derived from that voltage over that resistor we'll calculate the current. And therefore I've measured this resistor. It's a nominal 1 ohm resistor with 5% accuracy. But it turned out 3 different multimeters assigned that this is a 1.2 ohm resistor. So could be also the precision of the multimeters, but none of them showed 1.0. So we'll go with 1.2 for our calculations for this resistor. Now the picture is a little bit different. You see the plus pole of the battery. It's connected via this resistor to this connector here. And now we can attach the oscilloscope clips to the 2 ends of the resistor to measure the voltage over this 1.2 ohm resistor when the battery is feeding the clock with current. So let's see. So as you see here, I connected the reference lead of the oscilloscope to ground, and the probe lead of the oscilloscope to after the resistor. So that will hopefully have the effect that when the clock is blocking for the 1 second, that there is the full potential of the 1.33 volts here across the whole thing, and we measure it with the oscilloscope. And then when the clock lets current through, then there is a voltage drop here, and we'll measure a drop in voltage here at the lead after the resistor, and then we can see how much that it drops, and we'll watch that drop carefully over time on the oscilloscope. I have it here in rolling mode, so we'll view that exactly when that happens neatly in time domain. So yeah, all I have to do is connect now this this plus circuit part up, ending here at the moment. We're done in a short, and then we'll meet. And there you have it. We have set the time domain to 200 milliseconds per unit. Perhaps you can do that a little bit coarser. Yeah, but then it's not so visible. And yeah, if I turn the precision up of the voltage vertical range, then it gets quite messy. This is quite a good thing. I think we have to stop it somewhere here, for example. And then with this we can calculate the time domain of what exactly happens here. So the third thing I think to note is what down below here our reading said. It says the minimum we measure is minus around 10 millivolt, and it says from peak to peak here, from peak to peak we are around at 17.6 millivolt. But that's a lot of, I think, because the thing is so blurry here measured. I would just say that this drop that you see here, I would just say that it is around 10 millivolt drop. I hope that's good enough. It must be good enough for the moment. So let's say the drop is 10 millivolt around. And then what we can worry also about is that we have here the duty cycle of this. So you see one section is 200 milliseconds, it's here H, you see one, so it's stopped here, the drop of the voltage. It's in fresh cycle starting here after the drop. Then 1, 2, 3, 4, 5. That's a second. That's really good, because that's a second of what happens in a second in our clock. Then you see the drop it's here, and we can estimate, okay, how much time is that? And I'm gonna look if I can do something like here with the duty cycle. So let's see what if I click around like this one, the white. It's already here. It says okay, and it says it's 142 milliseconds. That might be a tenth of a second or more. So a tenth would be half of a, that's not quite. So this is 200 milliseconds, so half of it would be 100 milliseconds, and 100 milliseconds is a tenth of a second. But this pulse here, it is not, it is less than 100 milliseconds. It is half of that around, and not quite. So half of 100 milliseconds would be 50 milliseconds, and I reduced that, I think, 50 milliseconds. Let's do it. So let's be generous. Let's say this is a 50 millisecond pulse. So let's say time of duty cycle is 50 milliseconds, and let's go with that. So we have a drop of 10 millivolts. So this means 10 millivolts we are like losing here from here to here. So we have 10 millivolts around our 1.2 ohm resistor. So we can say what is our current through there? It is current equals voltage through resistance. That is 10 millivolts drop divided by 1.2 ohms. So, and then let's calculate that. So we're back, and that is 8.3 milliampere around. And it's 8.3 milliamperes for 50 milliseconds. Okay. So in order to get our effective current, we need to, if we multiply the 8.3 milliamperes times the 50 milliseconds, we get the amount of electrons flowing through the system. Then we divide that through the time that these electrons take, these loads more general, and then we land at the effective current. And what we also can do mathematically is to divide just 50 by 1,000. That is then 1/20th, and so you just divide then in some 8.3 by 20, and you get what that is. Okay, and with that we land at 415 microampere. And yeah, so let's compare that to the other number we got here. We had here 650 microampere. That would mean we have like around a third more. The thing will, we can calculate how much longer we will run if we go from the 1500 milliampere hours again. So we have 1500 milliampere hours divided by this 415 microampere. Let's see what that is. So I did that, and it comes out that the clock can run in 3614 hours. We can divide that by 24. Do I write 24 hours per day? And if we divide that, we get the clock runs 150 days. Okay, so 150 days, that's not quite half the year I was talking about. But I think we were a little bit generous also with the half, with this here, 100 milliseconds, 50 milliseconds. Perhaps these are like, the pulse is only like 30 milliseconds or something. And then we would be interesting to do this calculations with 30 milliseconds again. Let's just, for the sake of it, let's do it, because I think it runs longer than 150 days. Yeah, and I did the calculations with 30 milliseconds, and it turns out that then it will be 5,435 hours of runtime of the clock, and this is 226 days. And this means every quarter a year this clock battery must be changed around. And that's pretty much, that's a value I can be friendly with. So we've seen, okay, our measurement granularity really decides here about a lot of days, a lot of hours, thousands of hours. And I think I'll try to get the oscilloscope to run more exactly, to measure exactly that drop here. So hey, I did a little bit of triggering here, and so let's catch this one. And as you see, it is around 10 milliseconds per horizontal division. So that pulse here is really exactly like 30 milliseconds, all a little bit rough, but you see 3 divisions here, 30 milliseconds. And perhaps let's try to catch another one. So this guy to the right over there, let's bring him to the party here. Another, let's also expand, and let's see. Yeah, and that guy is also 30 milliseconds. So it's pretty much the party of the 30 milliseconds here. So what we calculated last, so 226 days is the thing, and if we divide that by 336 days, then how often do I have to change my battery? So I calculated that, and it is around every 7 months I have to exchange the battery. So that's really a cool. So the 30 milliseconds stand pretty much. What we could go into is the 10 millivolts again. Here, as you see, where is it? Here, that's 5 millivolts here. And I think, if I look at it correctly, I have to bring it down. Yeah. So you see the center drop. If we really take the center here, from here the center, and to here the center, and that's around, I don't think it is 10 millivolts. This vertical division is 5 millivolt. It is around, I think that is 4 millivolt, better said. And that again changes the whole game. So we're pretty sure, I think, about the 30 milliseconds, and I think we can be calculated with 4 millivolt, giving us, where does that impact us? So then not 8.3 milliampere, but we're going down, like we're taking 4 out of 10. So this will be 4/10 the value, so not 8.3 but 4/10 of that. And then when you go into the, we have to take with our 30 milliseconds, we have to 4/10 of the 8.3, and so we have to take 4/10 of the 276. So I'll do that and finish off the journey. So what I said was we have to take like 4/10 of the microampere here, but we can also not do it and just put it here where the microampere are used. And if you have in the denominator 4/10, then in the end calculation it will turn out as a multiplier of 10/4. So it will turn upside down. That's basic algebra. So 4/10 in the denominator will turn out as 10/4 in the numerator. So we can just simply multiply the 10/4 of the 226 days as a rough rounded result, and then we land at. So the 226 is the rounded result, and we really precisely rounded it, so not so much of a matter. You take that off times 10/4, and you land at 565 days now. And that gives you, if you compare that to 365 days of a year, then 565 days mean you don't have to change your battery every 7 months, like it was with the 226 days. But now that we have so much more days, it means you have to change your battery every 18 months. And 18 months is simple, 1 year with 12 months and 6 months additionally. So 1.5 years I have to change the battery. And that is pretty much what is my experience. As you say, I started out in this video talking about, I have the battery for half a year or a year in there, and I think I have to, a year not change the battery. And now that completely matches my experience of 1.5 years. And as you see, the measurements we took were quite rough, and we averaged everything out here. Where's the middle line here? Where's the middle line here? Oh, it must be 4 around milliampere, but now it matches with my experience very much, and it's cool. So I hope you like this journey of my old wall clock. So to summarize, the current it draws, so that would be interesting. We haven't done that. To summarize my wall clock, it draws how much? It was 4/10 of 276 microampere. Let's just do that for a quick what that is. Yeah, back there. So this is 110 microampere around. So that's 1/10 of a milliampere. That's really cool. And because that over time it's so low of a current, you can really have a long time of joy with your wall clock, even though it's mechanic, as you might have seen. That's a mechanic clock. And yeah, you can have enjoy your clock 1.5 years because it draws around 110 microamperes. I still don't get it. It's a mechanical thing, and as you hear it, it ticks and ticks. And very amazing. And so I have to, in the future, I know that for my wall clock, I can have in a 1 hour in a year and a half, and I can reload it with a battery. Perhaps also it's interesting for you, these calculations, or you can also estimate, okay, how long will it take for me? But it will be roughly different for your clock, because I think the clocks are built quite inconsistently. Or if you have other experience, tell me in the comments. Perhaps the mechanics of such clocks are somewhere made centrally. And we can look at mine for a quick. What is it here? It is search Cipeva GmbH in carbon. There's a quartz in there, something. I don't know if this is only I think this is only the distributor, is it? The Cipeva GmbH. We could look into this thing, really. Would be interesting. But let's leave that for another video. For the moment, if you have any experiences with such mechanics or found this interesting or something, you can always thumb up or like me, subscribe my channel, and then we'll meet in the next one. Bye bye.